Okay, how's everybody doing this morning? Yeah, little chilly out there, huh? Yeah, all right. So today we're going to start with a review of soldering. We talked about soldering last time, so we'll go over that just for a few minutes. Then we'll go on to our main topic for today, which is the fiber optic transmitter. So today you're going to start to build your own fiber optic communicator boards. So in the lecture, I'm going to talk a little bit about what the fiber optic transmitter is and how it actually works. And then in the lab, you'll get to start to solder that together. Then I'll go over the lab preview, which is going to be some instructions for how to actually solder that together. And then we'll go over and actually get to do it. For homework, I'd like you to work on the communicator crossword, which is on page 141 in your lab book, and also the communicator homework, which is on page 143 in your lab book. So please take a look at those. These will have some information that I'll talk about today. They'll also have some of the information about the fiber optic receiver board, which we'll talk about next time. So if you don't have all of the information yet, that's fine, but you can start taking a look at those. So any questions before we get going? Okay, then let's do our review of soldering. So we said that soldering is a way to join two components together, whether it's two ends of a wire or whether you're soldering a resistor onto a circuit board. You can use soldering to hold these components together. Now, there were two key things that you needed in order to get a good solder joint. What was one of those things?
Heat.
Yep, heat. And what was the other one? Cleanliness, exactly. So you need to have a clean surface to work on, and you need to have enough heat. And if you have those two things, then your joints should come out pretty well. So for cleanliness, there were a couple of things that we could do to help keep everything nice and clean. First of all, we could wash our hands before we do soldering, because any dirt or oil that might be on your hands could get in the joints. Also, you wanted to use a little bit of the alcohol with the brush and one of those wipes. That helps to clean up the surface before you start working. And then finally, you wanted to make sure that you use the flux or the rosin core solder, and that you use that solder while it's still smoking a little bit, because that indicates that the rosin is still in the middle and it hasn't completely evaporated. So if you can do those things, you should end up with a nice clean joint. And then the other thing that we need in order to have a good solid joint is we need to have enough heat. So basically the reason that we need heat is because we don't want to just melt the solder, we want to actually melt the surface metal on the component or the board as well. And in order for that to happen, your surfaces need to warm up quite a bit. So the way that we ensure that everything gets nice and warm is that we bring the solder in from one side of the joint, or the soldering iron in from one side, and then the solder in from the other side. So we bring the soldering iron in and we leave it for a count of 5 maybe, and then we bring that allows everything to come up to temperature. And then we bring the solder in from the opposite side, and we only touch the solder to the components or the board. We don't touch the solder directly to the iron. That way, the solder won't melt until everything is warm enough. So by bringing the solder in from the opposite side, we make sure that everything's warm enough, and you get a nice good solid joint that way. So any questions about that? All right, so cleanliness and heat are the keys for soldering. So then let's go on and talk about our main topic for today, which is the fiber optic transmitter. So let me just remind everyone what we're talking about here. Each one of you is going to be building your own fiber optic communicator. And that includes two boards. You have a transmitter board and a receiver board. So the purpose of this whole thing is that the transmitter board has a microphone on it and the receiver has a speaker. So when you speak into the microphone, you should be able to hear your voice coming out of the speaker. Test, test, 1, 2, 3, check, check. So that is the idea. So I'll pass this around so everybody can take a look at that. Yeah, it has a little bit of feedback if you get them too close together. So today we're going to start working on the fiber optic transmitter board. So we're going to start to put that together. So what I want to do here, first of all, is I want to show you the circuit for that board and tell you how that works. And the reason that we want to go into this is because this board can be a tool to help you get a job in the electronics industry. If you go on an interview and you can bring this circuit board along and show your employer what you've done, that's great. And if you can tell that potential employer how that board works and what it does, at least at a high level, that's even better. It shows that you really understand what's going on, and you have some understanding of how electronics work and how circuits work. So that's what I want to do. Today I want to show you a little bit about what this circuit is and how it works so that you can explain this to somebody else if they ask. So this is the circuit for the fiber optic transmitter. Now, if we look at this circuit as a whole, it can be overwhelming. There's a lot of different parts there, and they're connected in a lot of different places. And so if you look at this as a whole, you might have a hard time understanding what's happening. So when we look at circuits, in general, we don't look at them as a whole. Instead, we break them down into sections called stages. And we look at each stage by itself. And then we kind of see how the stages work together in order to create the whole thing. So let's look at this. Let's break this down into stages. So this is the same circuit, but now it has been separated into stages. Okay, so you can see that there are 4 main stages here. And if we break them down like this, hopefully it's a little bit clearer what's going on. So we have the power stage, the input stage, the amplification stage, and the output stage. So the power stage, we'll just do kind of a quick overview of each one, and then we'll dive in and see how each one works a little bit more. Okay? So the power stage, oh, there you go. If you get them too close together, they have a little feedback there. The power stage provides power for the whole circuit. The input stage takes the stimulus from the outside world and turns it into an electrical signal. The amplification stage takes a small electrical signal and makes it bigger. And then the output stage takes that electrical signal and turns it into some other type of signal or energy that is leaving the board. In this case, it turns it into light, which shines down the fiber optic cable and ends up at the other board. So this board really has these 4 different sections. The circuit has these 4 different sections that work together in order to achieve its goal. So does that kind of make sense, how we break it down? All right, so then let's take a look at each one of these sections with a little bit more depth, a little bit more detail to understand how it works. Let's start with the power stage. So the power stage has this component over here. What do you suppose that component is? Yeah, the power supply, and in this case, what's providing the power for this device?
Battery.
The battery, exactly. So this is the battery over here. And then up here, we have a switch. And that switch is put in series with the battery. So when that switch is open, none of the power can get from the battery to the rest of the circuit. So what do you suppose the purpose of that switch is? It turns the whole thing on and off. Yeah, it's basically the on-off switch. It is the on-off switch. So we have the battery and then the on-off switch. And then over here, we have a capacitor that is in parallel with this battery. So we haven't talked a lot about capacitors yet, but capacitors work like reservoirs for power. They can be, you can put energy into them, and then they can store it, and then later on when you need it, they can release it. So, huh?
In a way, they're like batteries.
They are similar to batteries in that batteries store energy and capacitors store energy, but the actual physical makeup is much different. So batteries are essentially sheets of or pieces of metal separated by a chemical that transmits electrons from one to another, and they create their energy with a chemical process, whereas capacitors, they don't create any energy by themselves. They need to receive energy from an outside source, and they have an insulator between the plates. So anyway, but yes, they can. Both capacitors and batteries can store energy. Another difference is that batteries typically can store more energy, but they have a hard time discharging it very quickly. So there's a limit to the speed that the batteries can discharge their energy. So if you need a jolt of energy quickly, sometimes the battery can't really provide that, and the voltage of the battery might get pulled down. Whereas the capacitor can provide that energy very, very quickly. So that's one of the reasons that we have this capacitor next to the battery. The battery is there to provide sort of the long-term power, but this capacitor can provide quick bursts of energy if your circuit needs that. Like if there's a loud sound and your circuit needed to create a big electrical signal quickly, the capacitor could provide that energy to do that. So that's why we have this capacitor next to the battery. It helps to keep that voltage level at a fixed level there. And then over here, what is this component? Exactly, it's an LED. And then we have a resistor in series with that LED. We've seen that configuration before. Why do we put that resistor in series with the LED? Awesome. Why do we put the resistor in series with the LED?
So we believe the power to not burn the light.
Exactly. So we limit the current so we don't burn up the LED. So that's what's going on here. We have an LED and a current limiting resistor. So when the power is on and the switch is closed, the LED will be on. When the switch is open and the power is off, the LED will be off. So this is really just an indicator light to tell us when the power is on. And we can see that if we look at the board here. So this is the transmitter board, and you can see that this LED is on when the power is switched on, and then when I switch the power off, the LED goes off. Okay, so it's just an indicator light to show you when the power is on or off. And you'll notice that the battery is connected between this top wire and the bottom wire, and then these wires stretch out across the rest of the circuit. And you remember the voltage is constant along any wire. So this power stage has a ground or a 0 volt section here, and then that stretches across the rest of the circuit. So that provides 0 volts to the whole circuit, ground for the whole circuit. And then also the power stage is connected up here to this top wire. So that would be, this is a 9-volt battery, so that would be 9 volts up there. So, and then this wire stretches across the rest of the circuit up there. So that's how this power stage is able to provide ground and power for the whole circuit. Yeah?
The wire connecting the two, is that so that's a fiber optic wire?
This black cable between the transmitter board and the receiver board, that's a fiber optic cable.
Okay, and what type of what can go through that? Like pictures? Can like recordings go through it, or is it just audio? Or
well, so this is just a clear plastic cable. So that type of cable can be used to send data. If you're talking about internet, the many internet companies use fiber optic cable to send data. And what they do is they turn a picture or a video or a music file into a bunch of zeros and ones. And then they send those zeros and ones over the cable as maybe light and dark flashes. And so by doing that, they can take almost any kind of file and send it over the cable.
Because I know before, like HDMI cables, like certain cables could only do sound, or certain cables could only do like video without sound, or something like that. It was always both. So I was wondering what was different between those cables and that.
So many cables are made out of metal. Most of the stuff that we're talking about in electronics, we're talking about electronic signals, and those go over metal cables, typically copper cables. But the material itself is just sort of a medium that things travel through. So some cables are designed to carry audio signals. So like if you have a pair of headphones, they would have maybe a 1/8 inch jack on the end, and that type of cable is typically designed to carry sound.
So it's not that they can't do it, it's just that they're not designed for that task.
Right,
Okay.
right, exactly.
Okay.
Yeah. Yeah.
Why is the capacitor and the power state 47?
Right. So why this value? The answer is that it's kind of a trade-off. So the bigger the capacitor is, the more energy it can store, and the better job it will do regulating the power. So for that reason, you'd like to have a big capacitor. But at the same time, the bigger the capacitor is, the more room it takes up on your board, and the more expensive it is. So, so from that point of view, you'd like to have kind of a smaller capacitor because they're cheaper and easier to fit into easier to fit into the space. So it's a trade-off. So you want to find something that's big enough to regulate the power and meet your needs, but at the same time small enough to fit on your board and not be too expensive. So this 47 microfarad is kind of a middle ground. It's big enough to do what we need, but not so big that it's super expensive. Yeah. Yeah. So just a quick reminder for anybody, we still have the class split up. So this section of the class is doing the soldering, and the other section is doing other labs. So if you typically are in Fred's lab, you want to be over there. We're going to do that for the next 4 classes, including today, and then after that, we'll switch back, and whoever was in here doing the soldering with me will go over and be with Fred, and whoever was with Fred will come over with me. And that's just because we don't have enough soldering stations to do all of the soldering together at the same time.
So for typical threads, should we just have that?
Yeah, yeah. No, it's okay. So, yeah. So, all right. So that's the power stage, and then so next up we have the input stage. Next up we have the input stage here. So the input stage, like I said, takes the stimulus from the outside world and turns it into an electrical signal. So in this case, the stimulus is sound. We're speaking into the microphone, and we'd like to turn that sound into an electrical signal. So the way that this works is that this microphone acts kind of like a variable resistor. And when we speak into the microphone, the louder the sound is that hits the microphone, the more that resistance changes. So we can see that that microphone is in series with another resistor. So what we have is we have one fixed resistor up here, which is 20 kiloohms. And then we have the microphone down here, which acts like a variable resistor.
What's its range of resistance?
It centers around about 20 kiloohms, and then it goes maybe, between, say, 18 and 22 kiloohms, something like that. So let's say that up here, this top part is connected to the 9-volt wire up here, sometimes called a rail. So we have 9 volts at the top, and then this bottom part is connected to the ground rail down at the bottom. So that is at ground. Say that both of these resistors were at 20 kiloohms. What voltage would we have right here in the middle? Well, so what was another name for a circuit that had two resistors in series like this? A voltage divider, exactly. And we call it a voltage divider because it divides the voltage. And if both of the resistors are the same value, they each get half of the total voltage. So we got 9 volts total, so what's half of that? 4.5, exactly. So the voltage in the middle would be about 4.5 volts.
Wouldn't the voltage also be in a range? Because since that's variable.
Well, right, exactly. So if this was at exactly 20K, then the voltage would be at 4.5. But so if this goes slightly above 20 kiloohms, like you said, it causes this voltage to go up a little bit. And if this goes below 20 kiloohms, it causes this voltage to go down. And that's exactly how we turn the sound signal into an electrical signal. As we speak, we cause this voltage or this resistance to shift up and down, and that causes the voltage to shift up and down as well. And so that turns sound into a voltage signal. And that's the signal that we get right here at this point, which is right between those two components. So does that make sense? So that's how we are able to turn the sound signal into a voltage signal.
So in this scenario, is 20 kiloohms for a variable resistor is like the sound system is that off? Like nothing's being sent through?
Right. When no sound is hitting the microphone, this voltage is at just a steady 4.5 volts.
Okay, then so what is the difference in like speaking that makes it go down or up? Like,
Well-
is it like certain frequencies of your voice, or like how loud? Like if you're being really quiet, does it go down? Or?
Right. So that's a great question. So what actually happens? So first of all, let's talk a little bit about what sound actually is. Sound is actually changes in air pressure. That's all it is. So we can hear this tremendous range of different types of sounds. We can hear other people speaking and understand their words. We can hear an orchestra playing, and we can pick out, 10 or 20 different instruments that are all playing at the same time. It's this extremely complex mechanism that we hear, but really all it is sound is just changes in pressure. So when we hear sounds, even though we can hear all of these complex things in the world around us, all we're really doing is detecting changes in pressure. And we're detecting the frequency of those changes. So if we hear a really high-pitched sound, that's a sound whose frequency is really high. So it's changing very quickly. If we hear a low-pitched sound, that's a sound whose frequency is changing very slowly. So a high-pitched sound might look like this, a low-pitched sound might look like that. Volume has to do with the size of these waves. So a very quiet signal would have a small amplitude like this. A very loud signal would have a very large amplitude like this. So that's what we are detecting with this microphone. We're detecting, well, we're just picking up and measuring the pressure of the air quickly. And what we see is that when a high-pitched sound hits the microphone, the pressure changes very quickly. A low pitch causes the pressure to change slowly. A quiet signal makes very small changes, and a loud signal makes large changes.
So where's the 4.5 divided into that area, like in theory?
So
Because something has to be cut out, right? Like some sort of level of like loudness or frequency has to not be picked up. Was that right?
well, okay, so what happens is that we have a voltage that changes over time. So, and it's kind of centered, it is centered around 4.5 volts. So when no sound is hitting this microphone, we would see just a constant signal at 4.5 volts. When a quiet sound starts to hit it, we would see the signal kind of go up and down a little bit. And then when a loud sound hits it, the signal might go up and down more, like that.
Okay.
Yeah. And that's why we have the signal centered at 4.5 volts. If we had it centered at 0 volts, then we would kind of get maybe and we were trying to record signals, we'd get maybe the top part of the signal, but half of it would be cut off.
Okay.
So we have it centered right in the middle of our voltage range so that we can get the higher, the high pressure and the low pressure parts.
And then it kind of has like invisible dotted lines where the top and the bottom of what it can pick up is, right? Like the 22 and the 18K resistor levels.
Right. So I mean, yeah. So I'm making this bigger so that it's more easy to see, but that's a good point. The signal coming out of this microphone is actually very, very small. So if we said that this is 9 volts up here and this is ground and that's 4.5 in the middle, then the signal coming out of the microphone is actually very small. So it might be, mostly constant, and then it might go up and down a little bit, and that might be a big signal. Then smaller signals you couldn't even see. So it would look, something like this. It's very small. Yeah, it looks almost like a straight line, and we can see this when you build your board. You'll notice that at a number of different points on this board, there are these little things labeled TP. TP stands for test point. And those are points where you can hook up your oscilloscope and actually measure the signal. So you can see that there's a test point right here at this point between the microphone and the resistor. So you can actually measure the signal at that point to see what it looks like. So, yeah, I recommend that you do that after you build your board. So anyway, so this is what's going on. This is how we create the electrical signal from the sound, and this is what the signal might look like. But as I said, this is a very small signal. It's not really big enough to do anything useful. So the next thing that we want to do is we want to make it bigger. But actually, before we get there, there's one more thing, and that's this capacitor here. What happens is that capacitors allow high-frequency signals to pass through them, but they block out or absorb lower frequency signals. So the reason for that is because this, like I said, when there is no signal, no sound hitting this microphone, the voltage is constant at 4.5 volts. So we don't really care that, exactly what the voltage level is at that point. All we really care about are these little variations in the voltage, because those little variations are the sound. So a constant signal that doesn't change, that has the lowest frequency of all. We say that a constant signal has a frequency of 0 hertz. It never changes. So if we want to get rid of that constant, unchanging part of the signal, we can use a capacitor to do that because it blocks out low frequency signals. So this capacitor allows that high frequency sound signal to get through to the other side, but it blocks out that low frequency constant signal that we don't care about. Okay, so that's what that capacitor is for. All right, so then we go on to the amplification stage to take that small sound signal that we care about and make it bigger so that we can do something useful with it. So this is the amplification stage right here. The main thing that is here that's doing most of the work is this thing right in the middle. It's labeled 741. That is something called an op-amp, an operational amplifier. It's a little chip that's actually doing most of the work. So this chip is designed specifically to amplify signals. And the amount of amplification that it provides is determined by the components that you put around it and the way that you put those together. And we'll talk a little bit more about op-amps and what circuits we can make with them later in the semester. But for right now, the important thing is that this is an op-amp, and it's providing a gain of about, I think, 200. So that means that the signal that's going out is about 200 times bigger than the signal coming in. Okay? Yeah.
What was the full name of op-amp again?
Operational amplifier.
Thank you.
Yeah. So, yeah, we'll learn about them more later in the semester. They're really versatile chips. You can use this one chip to create lots of different types of amplifiers. But for right now, this just provides an amplification to our small signal. So we get the small signal coming in, then we amplify it, and we get a bigger version of the signal going out.
Are we going to be making this whole then?
Well, you're gonna.
Or or make part of it?
You are going to solder all of the components into this circuit board. So the circuit board has already been created for you, and the circuit board essentially provides all of the connections. So all of those connections are etched into a copper layer to create essentially little wires on the surface of this board that provide all of the connections between the different parts. So what you will all have to do is solder the parts into the little holes and spaces that are provided. And then once you do that, the other connections will be made by the board. Yeah.
Does each person work on their own?
Yes.
Okay.
Yep. And these will be yours to keep when you're done. So, yeah. Yep. The one other thing that I wanted to point out about the amplification stage is that it has this other switch in there. And this other switch is a switch for a test mode. So when the switch is in one position, this amplifier acts normally, and it just takes the small signal coming in and makes it bigger. When the switch is in the other position, it creates a test tone. This is a large signal that gets sent out. It's a large oscillating signal that gets sent out through the fiber optic cable. And this is useful for a couple of things. First of all, it can show what it can demonstrate that at least the amplifier part of this board is working. And it can also be used to create that large signal that can be used to test out the fiber optic receiver. So let me show you what that is. So it's a really loud, annoying screech is what it is, okay? So we turn this on, and then this switch up here is the test mode switch. So yeah, it makes that awful screeching sound, okay? And it sounds really bad, but it's actually very helpful. It's a large signal that's easy to see and easily verifiable. So that's why we have that there. So that's what that switch is. It's a test mode switch. So any questions about the amplification stage? Okay. And then finally, we have the output stage. And the output stage takes the electrical signal and turns it into some other type of energy that gets put out from the board. In this case, we're turning it into light that we can shine down the fiber optic cable. So, the way that this works is that we have this little LED up here, and that LED represents it represents the little light that shines down the fiber optic cable. Okay, and then we have this component, and this is called a transistor. And a transistor acts like a sort of a dimmer switch that is controlled by an electrical signal. So we have this electrical signal coming in, which is our amplified sound signal, and then it's connected to this dimmer switch. So when the signal goes up, it makes the light brighter. When the signal goes down, it makes the light dimmer. So when the signal varies quickly with the sound, it makes this light brighter and dimmer and brighter and dimmer, and that shines down the cable, and that's our signal that we're sending to the other board. So that's how the output stage works. So any questions about that?
And we have another board that we're gonna have to do, right?
Yeah, so this is all the circuit on the transmitter board. We have another circuit on the receiver board, and we'll talk about that next time.
So are we supposed to finish all of this today?
No, you don't have to. So what we're going to do is we're going to have 4 classes to work on this all together. So to work on 2 boards. So we want to give you that time to work on these because we want you to really do a good job and make these look nice and clean. Because like I said, these can be tools to help you get jobs out in the real world. So we want you to take your time and really do a good job on these. So you will have the lab periods today and then for the next 3 classes as well to work on these 2 boards. Yeah. Yes?
Is there a place for us to review this layout in case we're trying to reference it while we're building?
Yes. So this is part of the fiber optic communicator PDF. So I'm going to go through that in just a minute also when we do our lab preview. Yeah. And that's available on Canvas, and yeah, you'll be able to see that. Yeah, other questions? Yeah.
In the amplification stage,
Uh-huh.
are the 10 kilo ohm resistors that are they meant to regulate the voltage going into the op amp?
Kind of. So you have two 10 kilo ohm resistors in series. So again, they act like a voltage divider. And you have this capacitor in parallel with that resistor. So again, that helps to stabilize that voltage at this point. So really, these two, what they're doing is they're creating a stable voltage of 4.5 volts at this point right here, which is connected to one of the inputs of the op amp. So it's just creating a stable 4.5 volts there. And then the op amp it's really amplifying the difference between the incoming signal here and then that voltage there.
So it's not using it as power, it's using it as a reference voltage.
Exactly. Yeah, it's a reference voltage. Yep.
Thank you.
Mm-hmm. Yeah.
Sorry, one last time. The
Sure.
transistor, what does it do at the output stage?
The transistor?
Yes.
So it acts like a dimmer switch that's controlled by an electrical signal. So, yeah. So it brightens or dims this LED up there. Now, talking about power for the op amp, there is actually a power input and a ground input to the chip here. And on the diagram, you don't see the wires actually going all the way up to the power rail or all the way down to the ground rail, but they are labeled power and ground. So this is a convention that happens in circuit diagrams sometimes, especially when they start to get more complicated. You can imagine that sometimes it would be sort of confusing or difficult to draw the wires going from where they start to where they need to be. Because if we tried to draw the wire going from here all the way up to power, we'd have to draw it across the capacitor and across the resistor, and it would kind of get in the way. So sometimes instead of drawing the wire all the way up to where it's supposed to go, it gets drawn part way, and then the label is applied to that wire. So when this one is labeled power there, it indicates that it's connected to the power rail up there. And this one is labeled ground. It indicates it's connected to the ground wire down there. So the op amp is getting power and ground, even though we don't see the wires extending all the way down there. So, yeah. So, any questions about that? Yeah.
What's the purpose of the 200 kilo resistor in series with the capacitor?
So these components determine what or how much amplification the op amp provides. So choosing different components would result in different amounts of amplification. And we'll talk more about that later in the semester when we go into some of the different types of circuits that you can make with an op amp chip. Yeah. Yeah, other questions? Okay. All right, then let's get into the lab preview, and we can talk a little bit about how we're actually going to put these boards together. All right, so everybody is going to get a kit that looks kind of like this. It's got all of the parts inside of it. It's got 2 boards, and they look kind of similar to each other. The way that you can tell them apart is if you flip them over. This one says transmitter on it. The other one says receiver. So if you look on the back of the boards, they will tell you which one is which. So this is the transmitter, and this one is the receiver. Okay, so today we're going to be working on the transmitter. So on Canvas, you will find a link to the instructions. So if you go to assignments, and you can search for assignment, and you can search for transmitter. You click on the fiber optic transmitter. This will have a link to the communicator instructions. You can download that, and that's what I'm going to go through right now. So the instructions. All right, the instructions look kind of like this. So the first part is the introduction. This talks a little bit about the background for the kit and how to use it. And then we get on to the assembly tips. So let's just go through these for a minute. So generally, you always want to wear safety glasses. We know that. In general, you might want to start by soldering in the resistors because they are the shortest components physically. They're shorter than the rest. If you solder in one of these capacitors that's half an inch tall maybe, it can kind of block your soldering iron from getting down to the lower components. So you typically want to solder in the shorter components first, and then you can move on to the larger components later. So start with the resistors. There are some electrolytic capacitors, and they are polarized. So the electrolytic capacitors are these things that look like little soda cans. So like this, for instance. So this is an electrolytic capacitor, and it's polarized. That means that one side needs to be positive, and the other side needs to be negative. What happens if you hook them in backwards? Yeah, they will explode. They will blow up like tiny firecrackers, believe it or not. Ask me how I know. So these have a positive side and a negative side. So if you look, they're labeled clearly because this is a big issue. So you can see here, this side of the capacitor has this little minus symbol, this negative sign on it. That's the negative side of the capacitor, and you can see that it's closer to one of the legs. So that leg is the negative leg of that capacitor. The other leg will be the positive leg of the capacitor. So when you go to solder these into the board, you might be soldering it into this hole, for instance. You can see that this is labeled C for capacitor. This is C2. And you can see that one of the holes is labeled with a little plus sign for positive. So you would solder the positive leg of the capacitor into the hole with the plus sign. You would solder the negative leg of the capacitor into the other hole. So any one of these round electrolytic capacitor places has a positive side labeled. Okay, so make sure you solder those capacitors in the correct orientation. You can use tape to hold the larger components in place. So we will have some masking tape over there, and sometimes that can help to hold in the larger capacitors and things like that. You need to solder the socket into the board and not the chip. So we talked about that little op amp chip. You do not solder the op amp into the board. The reason for this is because the op amps can blow out, or they can go bad. And if they have 8 legs on them. And it's a real hassle to try and desolder 8 different things at the same time. So instead of soldering the chip directly into the board, we have this little socket that you can use. So what you do is you solder the socket into the board, and then you just push the chip into the socket. That way, if the chip goes bad, you can just pull it out and pop in a new one, okay? So let me show you that. So this is the spot. This is the spot right there where the chip is going to go. You see it's labeled 741. You're going to solder this thing into the board. This is a socket. So you can see it's got little legs that stick out the bottom, and it's got little holes on the top. So you're going to solder this socket into the board, and then after that's soldered in, you're going to take this chip that looks like this, and you're just going to push the legs of the chip into that little holes on the top of the socket, okay? Again, that way if anything goes wrong with the chip, you can just pull it out and pop in a new one, okay? The other thing to be aware of is that this chip has an orientation that it needs to go in. So if you look at the board, you can see that there's this little U-shaped indentation on one side of the marking. Everybody see that little U? Yeah. On the socket, you can see that the socket has its own little U-shaped indentation. So you would line up that U-shaped indentation on the socket with the U-shape on the board. And then the chip also has a little marking. So with the chip, it's this little circle. So you see this little circle there. Some chips have a little circle, some of them have a little U, but in any case, that goes towards the U-shaped marking on the board. So that's how you know which way to put the chip into the board. Okay? So when you solder those together, you want to make sure that all of those things line up. Okay? All right. And then the next thing is the battery terminals. So we're going to connect the battery to the board. So you can see that the battery is going to be plugged into these 2 little terminals. Now, of course, the battery has a positive side and a negative side, and you need to make sure that those are in the correct spots. Now, if you look at these little terminals, you can see that one of the terminals is smaller and the other terminal is bigger. Okay? If you look at the board, you can see that when you look at the spots for the battery terminals, one has a smaller solder mask indication here, and one has a larger silk screen. So the battery terminal with the smaller hole goes next to the spot with the smaller solder, the smaller silk screen. So it goes like that. And then the battery terminal with the larger hole goes next to the larger silk screen. It goes like that. Okay? So make sure that you put those in the correct positions, otherwise it's not going to work. Okay? So those are the general instructions. Now we have a couple of instructions that are specific to the transmitter. So when you put the chip in the board, make sure that you use the 741 chip, not the 386. So we have this 741 op amp that we're using for the transmitter. We also have a very similar chip that we are using for the receiver. So let me see if I can find it. So these are the two chips. You can see that they look very, very similar to each other. So how can you tell them apart? Well, if you look very, very closely, they actually have writing on the chips. So, yeah, you have to get it in just the right light. But if you do it just right, you can see that they have writing on them. So this one says UA741CP. So you might have to use your phone and shine a light on it, or we have magnifying glasses over in the lab that might help. They have illumination as well. But you want to look at these chips and try and find the writing on them. You can see that this one says 386N at the bottom. So you have to look at the writing and make sure you use the correct chip, because if you use the wrong chip, it's not going to work. Okay? So again, you're going to be putting these into the little sockets. So if you put the wrong chip in, you can just pop it out and put in the right one. But try to use the right chip. Okay? Now, this talks about the capacitor codes. So the larger capacitors, these electrolytic capacitors, are large enough to have their values written right on them. So for this electrolytic one that's 1 microfarad, it's just electrolytic, so there's no code on that one or the next one. However, some of these smaller capacitors are so small that they don't have enough room to have the full value written on them. So instead, they use a code that's kind of similar to the codes we use with resistors. So the 100 picofarad capacitor has a code of 101. And then the 0.003 microfarad is this 302. So what you will do is that these capacitors are the very small ones. So let me show you an example. So this is an example of a capacitor. And this one has writing on it, but again, it's just very, very small, so it's very hard to read. So if you look closely, you can see that says 332. So that code would be 332. So if we came back here, that would be a 332. So I think that one might be used in place of the 302. So anyway, that should be fine. But you're going to be looking for those little tiny codes on there to tell you which type of capacitor to use. Okay, so that's what you're going to be looking for. So that's all that I wanted to say about the about assembling this. Oh, one other thing. There's a microphone for this board. So the microphone receives the signal. This is a very small microphone. It's called an electret microphone. And this is what the microphone looks like. Okay, you can see that it has two wires that are sticking out of the bottom. Well, it's kind of hard to see from that angle. It has these two wires that are sticking out of the bottom, and they're not exactly centered in the case. So they're kind of on one side of the case. So the hole for the microphone, or the spot for the microphone, is right here. And you can see that the two holes for the wires are kind of off to the left-hand side of that circle. They're not directly in the middle. So what you're going to do is when you put the microphone in, you just put it in so that the wires in the bottom line up with the holes, and the microphone fits into the board kind of more or less in the middle of that circle. If you were to put it in backwards, it would be like sticking way off to the side, and it would be like that. So don't do that. Just put it in the orientation where it fits down into the circle, and then you should be doing just fine. So yeah, so you put it in kind of like that. It fits right in the circle, and that's the way it's supposed to go. So questions about that? All right. And the same thing for the transistor. You can see that the transistor is kind of in a D shape, and you're going to just put it in so that the body of the transistor lines up with the sort of D-shaped outline there, and then everything will be fine. Oh, actually one more thing. It says to use the blue fiber optic holder that contains the infrared LED. So over here, this spot up here is the spot for the fiber optic transmitter LED, the fiber optic LED. That is this thing right here. So this thing just fits down with the wires into those holes, and you're just going to solder it right onto the board like that. You'll notice that this is the blue one, and the board is also labeled blue. So it's talking about the blue component here. There is another very similar component. It's the same size and shape, but it is black, and we're going to use that for the receiver. So make sure that today when you're working on the transmitter, you use the blue one. Okay? If you solder in the other one, it will not work. All right, so you need to make sure that you use the blue one here, like it's labeled.
What's that component called?
This is the LED. Or, let's see what we call it in the fiber optic holder. So it's actually a couple of things combined. So in the middle, there's a little LED that points directly out there, but this blue plastic housing around it is actually a holder or a connector for the fiber optic cable. So each kit will come with a fiber optic cable that looks like this. It's kind of this black cable, and when you've soldered everything together, you'll be able to take this cable and feed it into the holder. Then you can just twist the collar on the holder, and that'll secure the fiber optic cable in place. So this plastic piece provides the holder for the cable as well as the LED inside it. Okay, and the black one is a receiver. So that's why they're not interchangeable. This blue one is an LED that creates the light. The black one is the receiver that picks up the light. So you can't just swap them out. So that's what's going on there. So any questions about that? All right, so that's what I wanted to say about the fiber optic transmitter. So let me take attendance, and then I'll let you go.